Welcome back, and we're continuing talking about electromagnetic radiation, and let's see how they get formed. Okay, suppose this is the plane at which they are formed. So if I have got a wave like that, if this one represents the electric field wave, okay, then there shall be at right angle to that, I would have this. Okay, at right angle to that, I will have that. But what we need to understand here, sorry about that, let's leave that one out. This one is at a right angle. In other words, there is a right angle here between this one and this one. This is the electric field, and this dotted one must be the magnetic field. They oscillate together at right angle to each other. So the EM radiation, the electromagnetic waves, are formed by oscillating electric and magnetic fields. One part is electric field, the other one is magnetic field. Okay? And next, electric and magnetic fields oscillate at right angles to each other, just like I've shown you in that diagram. And they also act at a right angle to the direction of propagation. What does that mean? It means that if this is the direction of propagation, this one is at right angle in that direction, and this one is at right angle to the direction of propagation on the plane. So they are like that, okay? This is the electric field, this is the magnetic field at right angles to each other, okay? Now, these EM waves, electromagnetic waves, move at a speed of 3 × 10⁸ meters per second. Okay, that is the speed at which they move, and they can move, of course, in a vacuum. They do not need a medium to travel in. They can move in a space without air, a vacuum. EM waves obey the wave equation. And what is the wave equation? You must know what it is. This is the wave equation. C equals F lambda. Okay, so that is what electromagnetic radiation is all about. But then now let's try and look at the current, because in current, that's where charges are moving, and then how the magnetic field is created around current carrying conductors. A current carrying conductor creates a magnetic field around itself. The right hand rule is used to determine the direction of magnetic field. And what does this mean? Look, we use the right hand rule to determine the direction of the magnetic field. And how do we use it? The thumb must point in the direction of the current. So if this is a cable, it's a conductor carrying current in that direction, if I put my thumb in the direction of current, my curled fingers give me the direction of the magnetic field created by this current carrying conductor. So in this case, you will see my fingers curled like that. That would mean the direction of the magnetic field will be in that, as I move as the curled fingers are pointing, that will be the direction of the magnetic field as well. So one thing very important about magnetic field is that we need to understand it's three-dimensional. So you can't just say it's this. It means it's also that, okay? So it's this way, it is also this way, in that moving charge inside the conductor, okay? Now, determining that direction, I have said we make use of the right hand rule. Because we've got only papers to show to draw things to show how current is moving in a conductor. If current is moving out of the page, okay, all right, coming out of this page here, I'm going to have a dot like that representing it. So because it's coming out of the page, let's see how the direction must be determined. The right hand rule. Out of the page this way, thumb pointing in the direction of current, my curled fingers are in that direction, and therefore the direction of my magnetic field is that way as indicated by the arrows in that drawing. And these lines here represents the magnetic field around that conductor. If the current is going into the page, we make use of an X to show that the current is going into the page. So in my case here, I will have that representing the current into the page. And because the current is into the page, just look at my palm here. The thumb pointing in the direction of current into the page, my curled fingers giving me the direction of the magnetic field. So hence I have that drawing in that way, showing the direction of the magnetic field. So the cross shows a current going into the paper, and the dot shows current coming out of the paper. So that for now gives us an introduction into the electromagnetic fields, or the magnetic field created by a current carrying conductor. See you in the next section.